Hello, students, and welcome to week 5 of our fourth marking period. We're going to today continue to look into how to solve basic trig equations. By that I mean trig equations that are of the first degree. And today we're going to part 3, where we're going to find out how do we find all real solutions to a trig equation. Now, up until now, our focus has been on finding solutions to trig equations that are between 0 and 2 pi radians. So we're trying to find the solutions that are in the first cycle through the unit circle. But what happens when the problem doesn't limit the domain? And instead we're asked to find all real solutions to a trig equation. Well, I have up here a sample, and we're going to go through what we need to do. So we have 3 sine of x minus 1. Up until this point, we've been doing these questions purely algebraically. But I want you to look at this graphically and see if that can give you a hint of what we have to do to solve this equation. So I have up here Desmos, and I have a graph up here, and I'm going to split this equation. I can rewrite this equation as instead y equals 3 sine of x minus 1 and y equals 0, I can set each side of this equation equal to y, and then graphically the answers are going to be the intercepts or the intersections of those two graphs. So let me plug this into my Desmos. I'm going to have my first equation. I'll call it f of x here. That's the same as y. F of x is 3 sine x minus 1. And that looks about right. That's what we should expect of a sine curve. And then we'll have a second graph, g of x, same thing as y again, equals 0. And now you should see that I have two lines here. The y equals 0 is going to be my blue line, and my y equals 3 sine of x minus 1 is this red sine curve. And the solutions that I'm going to get are these intersection points here. And as we would expect for algebraically for the answer, where we would have this solve into sine inverse of 1/3 would be what our x is. So there, since we have a sine and it's positive, we would expect the first two solutions in 0 to 2 pi would be someplace here in the first quadrant and then also in the second quadrant. And we see that from this graph. But what else do we also see from this graph? Where do our solutions come? Our solutions, we're going to see, they come at regular intervals, which should make sense since our sine functions are periodic. The very definition of periodic functions is that they'll have the same y values at regular intervals for our x inputs. So here I have this value here. If I go 2 pi, I get to my next periodic value. If I go 2 pi more, I get to my next periodic value. So recall when we were doing the graphing that the base sine and cosine functions have a period of 2 pi. So that means that once we figure out what those first two values are, those first two x values, now all we have to do is add multiples of 2 pi to each of those to get all of our solutions. So that means that overall, if I have initial solutions x1 and x2, right? Whatever these are, let's say my x1 is 0.34 and my x2 here is 2.80, then my general solution is going to be that all solutions to this equation are x equals 0.34 plus 2 pi, which is my period, times n, which is just some integer. Can be any integer. And then my other solutions are going to be 2.80 plus that 2 pi n. So for any sine or any cosine, my solutions are going to be that x is going to be equal to some x1 plus 2 pi n and x2 plus 2 pi n. And that's going to be based on how we've been solving these equations up until now. That's going to be my x1 and x2. And that's sine and cosine. But we really haven't graphed much with the tangent. So let's see what period the tangent's going to have. So here I'm going to go y equals tangent of x. And there we go. Those green curves, that's what our tangent looks like. And now here, our period is going to be determined not by maxes and mins, like we have in the sine and the cosine function, but rather just where we hit the same y value in each interval. And here, the tangent doesn't have a max and a min, but it always follows this same curve. It's always going from negative infinity up through 0 and into positive infinity. So we can determine the period of the tangent by looking at where we hit these same y values in each period. And here we have 0, 0. We hit the origin. And the next time we hit that 0 for our y value, we're pi. The next time after that, we're 2 pi. We can go back to negative pi and go back to negative 2 pi. So that means for the tangent, our period's going to be pi. So whereas for the sine and the cosine, I can write my general form as x equals x1 plus 2 pi n, x2 plus 2 pi n. For the tangent, I can have it much simpler than that. All I need to have is that it's going to be, so this is sine and cosine. For my tangent, all it's going to be is x equals x1 plus pi n. All right. Because my second time around, my second value is going to be at the 2 pi value. So this is a good thing to notice too when we're solving the tangent type problems, is that even if we're going from 0 to 2 pi, I only need to see that one value for the arctan in order to figure out every single value for the arctan. Right? So here, it's all based on the period for our general solution. Now, cotangent follows along with tan, secant and cosine follow along with secant and cosecant follow along with the sine and the cosine. So let's give it a try on another problem. Okay, we have one right here. 4 tan of x equals 4 tan of x plus 4 equals 0. I'm going to do this one algebraically. So if I bring my 4 over, this is going to turn into 4 tan of x equals negative 4. Thus, tan of x equals negative 1, which gives me an x is equal to tan inverse of negative 1. And now if we plug this into a calculator, we're going to find out that x is actually going to be equal to the value the calculation is going to give us is pi over 4, or negative pi over 4. Okay. Now, when we do the general solution, we tend to want to choose the first positive solution to it. So I'm going to go ahead and add pi to this, because that's what my period is for my tan. And my x1 in this case is now going to be 3 pi over 4. Our general solution now, our all real number solution, will now be that x is going to be equal to 3 pi over 4 plus pi n. And it's just pi here because we're dealing with the tangent. Let's give the other example in the notes a try. Okay, here I have my cosecant function, and I'm going to solve here. All right. So I'm going to have that cosecant of x is going to be 2 over root 3. Remember, I'm going to now take the reciprocal of both sides. So that's going to tell me that the sine of x is going to be equal to root 3 over 2. And I'm looking for x values where the inverse sine of 3 over 2. It turns out for these, this is also another common angle that we have, and this is going to be x equals pi over 3 and 2 pi over 3. Right? Because we have the sine, we're in the first and the second quadrants because our interior value is positive. And now just from our general all real numbers solution, we're going to have x is going to be equal to pi over 3 plus 2 pi, because that's the period of our function, of our sine function, 2 pi n, and 2/3 pi plus 2 pi n. And that is our general solution. Okay. Now, when we're doing these for the sine and the cosine, it's important to have both parts. We can't just combine these two together as something like 2 or as pi over 3n or something like that. It has to be pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n. So that's the first quick thing that I wanted to go over today. The other thing I want to do is talk about equations that involve multiple angles. And by multiple angles, I mean anytime that we have a trig function that the coefficient inside the function is anything other than 1. Right? Up until now, we had been dealing with equations like 4 sine of x minus 2 equals 0. I'm going to introduce where we can put a b value in. Okay? We can put a coefficient inside in front of that x. And there's really only one additional step that I have to take at this point. I'm going to show you how I'm doing this. And I'm going to solve this algebraically like I normally do. So it's going to become 4 sine of 2x is going to be equal to 2. I'll divide through by my 4. Means that sine of 2x is going to be equal to 1/2. And 2x is going to be equal to sine inverse of 1/2. Now at this point, I'm not going to be dividing through by 2 yet. I want to go ahead and plug that into a calculator. And that's going to get us pi over 6 and 5 pi over 6 as our two values. So this is going to pump out pi over 6, 5 pi over 6, because it is a sine function and it's positive, so it's going to be quadrant 1, quadrant 4, and this turns out that it's pi over 6, 5 pi over 6. And then I now have my general solution that I can put together. I know that 2x is going to be equal to pi over 6 plus 2 pi times n, or 5 pi over 6 plus 2 pi times n. And now I can go ahead and divide through by that 2. So I'm going to go ahead and divide everything on both sides by 2. And this will get me that my general solution at this point is going to be x is equal to pi over 12 plus pi n, or 5 pi over 12 plus pi n. So I do everything single step the same up until right here. And then the last thing is, after I find my general solution to this, I go ahead and divide it by the coefficient here to get my general solution to the overall equation. Let's do the example that I put in the notes. So I have 5 tan of 3x minus 2 equals 2 tan of 3x. So my first thing I'm going to do is group like terms. I'll bring my 2 tan of 3x over to this side, my 2 to the other side. So I'm going to get 2 tan of 3x equals 2. Tan of 3x then, if I divide through by 3, is going to be 2/3. So I'm going to get 3x is going to be equal to the tan inverse of 2/3. Plug that into a calculator, and I'm going to be told that 3x is going to be equal to 0.59. But I want to make this not just the specific to the first value that I get, to the first quadrant, but I want to make it all of my tans that I can have, all my tan inverses. So I'm going to add pi n to that. And now I go ahead and I divide everything through by 3. And that will get me that x is going to be equal to approximately 0.20 plus pi over 3n. Then if I just plug any integer in for n, I'll get all of the possible solutions to this equation. So go ahead, give the practice problems at the end of the notes a try, and find me in office hours if you have any questions.